We've all been there, right? You decide to write a quick script to automate some tedious chore.
Oh, yeah. The famous quick script.
Exactly. You're fully convinced it's going to save you like days of manual labor. And then cut to 5 hours later, you're just deep in the weeds of some broken environment setup.
Just fighting cryptic error messages.
Yeah. Fighting error messages and realizing you could have just done the whole thing by hand in like 10 minutes.
It is honestly the defining trap of modern software engineering. We get so obsessed with the elegance of the automation pipeline,
Okay.
we completely ignore the upfront friction required to actually build it.
Right.
The system architecture just becomes the job, rather than the actual task we set out to do in the first place.
And that friction is the entire focus of today's deep dive, but we are looking at it on a massively scaled up level.
Massively.
Yeah. We are digging into a set of personal notes from 2026 by a developer named Luck036. The document is titled Mastering clang-tidy, and the ambition here is just staggering.
It really is.
This developer set out to run static analysis across 27 different C++ projects. They wanted to resolve every single finding, purge all stale documentation across the board.
And do it all in a single evening.
Yes, all in one evening. Even if you've never written a line of C++ or, don't even know what clang-tidy is, this deep dive is for anyone who has ever tried to automate a task and hit that wall. Okay, let's unpack this.
Calling it ambitious is definitely an understatement. But what the source material really gives us is a masterclass in tackling overwhelming technical debt.
Right, because it's not just fixing syntax.
Exactly. It's a highly strategic look at how developers wield static analysis, navigate these just nightmare build systems, and actually deploy automation to keep their code sane at scale.
And anyone who has tried to wrangle a big multi-project ecosystem knows the tools usually fight you first.
Oh, constantly.
The code changes are usually the easy part compared to just getting the analyzer to, read the code base properly.
And the developer recognized that trap immediately. You can't just unleash a static analyzer on 27 repositories at once and expect anything other than a massive cascade of errors.
It would just blow up.
Yeah. So they needed the controlled environment first. They isolated a single pilot project called LDSCPE. It's a modern C++ library for low discrepancy sequence generation.
Which sounds incredibly mathematically intense.
It does, yeah. But the math wasn't the problem at all. The first bottleneck was simply getting clang-tidy to parse the code.
Just to read it.
Right. So the developer attempted the standard naive approach. They relied on CNAKE to generate a file called compilecommands.json.
And that file is pretty important, right?
It is the absolute lifeblood of clang-tidy. It maps out the exact compilation flags, the include directories, all the macro definitions for every single piece of the project.
So without it, the analyzer is just blind.
Totally blind. It has no context for how the code is actually being built.
But they ran into a wall right away because they were using MSVC, right? The Visual Studio CMake generator.
Yeah, and here's where it gets messy. The MSVC generator just silently ignores the request to emit that compile commands file.
Silently. Doesn't even throw an error.
No fatal error at all.
Oh.
It just doesn't produce the file.
Oh, wow.
So clang-tidy fires up, but it's missing all the dash I include paths. It can't locate third-party headers like fmt or method log.
And it misses the project macros, too.
Exactly. So the result is just this flood of absolute garbage analysis complaining about missing headers.
What's fascinating to me is that the tool doesn't even know it's broken. It makes me think of, trying to read a highly detailed map in a pitch black room.
That's a great way to put it.
The map, the clang-tidy static analyzer, is perfectly functional. It's right there in front of you. But without the flashlight, the include paths, the macros, you are just randomly poking at the paper in the dark.
What's fascinating here is the underlying philosophical clash between these build tools. Like the compile commands JSON specification maps perfectly to single configuration generators, like makefiles.
Because you pick debug or release up front.
Right, exactly, up front. But MSVC relies on MSBuild, which is a multi-configuration generator. It decides the build type later at compile time.
So CMake just doesn't know what to do.
Yeah, because of that architecture mismatch, CMake quietly drops the ball. The developer tools silently fail in a way that looks like they're working, but the context is just totally stripped away.
So how did the developer turn the flashlight back on?
Brute force. They abandoned the JSON file entirely and just built a manual recipe. They drove clang-tidy directly from the command line.
Passing everything manually.
Everything. Explicitly passing every single include path and compile definition using the dash dash extra ard flag. They just hard-coded the context.
Which actually brought up a massive warning in their notes. Once they had it running manually, they were very explicit about never using the dash checks equals star wildcard flag.
Oh yeah, that wildcard flag is incredibly destructive.
Really? Why?
Well, it overrides whatever carefully tuned config file the project has, and it just activates every single linting rule the LLVM team has ever written.
Oh no, so it flags everything.
The notes literally describe it as magic number noise.
Yeah.
You aren't getting valuable architectural warnings anymore.
He's just buried in nonsense.
Yeah, buried under thousands of pedantic notifications about, like, variable names or obscure formatting rules.
But why do you think developers fall into that dash checks equals star trap so often? Is it just human nature to want to turn every dial up to 11?
I think there is a heavy sunk cost fallacy at play, for sure. I mean, you fight the build system for half the day,
Right.
and when the analyzer finally blinks to life, you wanted to catch everything to prove the effing was worth it.
You want to feel productive.
Exactly.
Okay.
But in static analysis, signal-to-noise ratio is everything. If a tool flags 10,000 pedantic warnings, your team is going to ignore the report entirely.
But if it flags just a few critical ones, they'll actually fix them.
Right. And that is exactly what happened when they applied their manual recipe to the pilot project.
The LNDT project.
Yeah. Once clang-tidy could actually see the code, it didn't find a structural catastrophe. It narrowed in on exactly 6 issues.
Just 6 after all that setup.
Just 6. 5 of them were functional casts,
Right.
and the last one was a throwing static initializer.
Okay, let's talk about those functional casts. The code had expressions like double of X. Right?
Yep, double of X.
On a surface, that looks so clean and readable. Why was the system flagging it?
Because it's essentially a C-style cast wearing a different hat.
Yeah.
And modern C++ tries really hard to stamp those out.
So they had to rewrite them as static cast to double of X?
Exactly.
I still look at double of X and think it's fine. Why is the compiler so suspicious of a C-style cast?
Because a C-style cast is basically a sledgehammer.
A sledgehammer.
Yeah. When you use it, you tell the compiler to figure out whatever conversion path makes the types match, regardless of the consequences.
Oh, that sounds dangerous.
It is. It might perform a perfectly safe conversion, or it might silently do a dangerous narrowing conversion where you drop precision.
Or corrupt data.
Right. Or reinterpret memory in a totally invalid way. It just masks your true intent.
So the static cast is safer.
By forcing a static cast, you are writing a binding contract. You are explicitly telling the compiler and the next developer exactly what kind of conversion you expect.
And if the types change later.
Then the static cast will throw a loud compile error. The C-style cast would just quietly mangle your data.
Okay, so you want the code to fail loudly instead of silently. That makes sense. But the real tricky part in this pilot project wasn't the casts, was it?
No, not at all. It was that 6th finding, the throwing static initializer.
Right. They had a static variable being initialized using standard math functions like standard cos and standard sin.
And that is a massive red flag in C++.
Why?
Well, static variables are initialized during the startup phase before the main function is ever even called.
So before the program really starts.
Exactly. The runtime environment is incredibly fragile there. If an exception is thrown during that initialization, there's no active try-catch block to handle it.
So what happens?
The C++ standard mandates an immediate call to standard terminate.
The program just hard crashes before the user even sees a command prompt.
Instantly. And the analyzer flagged it because functions like standard cos are not marked. No, except in the standard library.
So the analyzer assumes it could throw an error.
Exactly, which makes the static initialization inherently unsafe.
So the developer tried to fix this by tricking the analyzer, basically. They wrapped the math in a lambda function and just slap a no except keyword on the lambda.
They assumed that guaranteeing the outer block wouldn't throw would satisfy the analyzer.
But the tool rejected it.
It completely rejected it because modern static analyzers don't just read the text. They parse the abstract syntax tree, the AST.
The notes call it the initializer subtree, right?
Yes, the initializer subtree. When clang-tidy evaluates it, it walks down every branch of that expression's AST.
Right.
Putting a no except label on the lambda is just like pinking the front door.
It still opens the door and walks inside.
Exactly. It walks into the subtree, sees the standard cause function sitting there without a guarantee, and flags it again.
The analyzer refuses to just take your word for it. So how did they eventually solve it? They couldn't rewrite standard cause?
They used a structural bypass. They extracted the math operations entirely out of the static initialization expression.
Into a separate function.
Yeah, they created a standalone helper function to handle the math, marked that new function as no accept, and then called it to initialize the variable.
Wait, they just moved the exact same standard cost call into a different function block.
Yep, but it changes how the AST is evaluated. When the analyzer parses the static initialization now, it walks the subtree and only sees a call to the custom helper function.
And because the helper is marked no accept.
The AST traversal stops right there. It evaluates the subtree as clean. It doesn't proactively cross boundaries into separate function bodies to double-check their internal logic.
Okay, I have to challenge this. We're putting the potentially throwing math inside a no accept helper function just to stop the analyzer from looking at it.
Yes.
It's like airport security. The scanner checks your carry-on bag, the subtree, but if you put a questionable item, like standard coast, inside a lockbox, the helper function, that the scanner is told is safe, it just glides right through.
That is exactly what is happening.
But is this helper function trick actually making the C++ code safer? Or is it just a clever loophole to get the analyzer to shut up? Because if standard coast throws inside that helper, it still terminates, right?
It absolutely will terminate. You've hit on the core tension of static analysis.
Uh-huh.
When you manually apply a no accept keyword to a function that calls potentially throwing code, you are signing a waiver.
You're taking on the risk manually?
Exactly.
Yeah.
In this context, the developer likely knew the specific inputs were tightly constrained and would never trigger a domain error in the cosine function. But your skepticism is completely valid.
Yeah, because if you just use it to silence warnings.
Then you are weaponizing the tool's architecture against itself.
Fascinating. Okay, so they proved the recipe on the pilot project. The configuration works, the AST traps are navigated. Now, the notes shift to the massive scaling effort.
Taking it from one project to 27.
In a single evening. Doing this manually would take weeks, so they brought in an army of automated agents.
They went with a highly parallel strategy. They deployed 3 survey agents across all 27 repos.
For what they called contextual grep at scale.
Right. One agent looked for infra issues, one for code-based casts, and one for documentation.
And the survey findings were super surprising. 19 of the 27 projects didn't even have code violations.
Their static analysis was totally clean.
But their documentation was heavily degraded, right?
Huh.
The read AMEs were telling users to enable an old, deprecated flag called uStaticAnalyzer.
Yeah, entirely stale docs.
Yeah.
So to fix this, plus the code issues in the other repos, the developer unleashed 8 parallel fix agents to automatically edit the files everywhere.
And that is exactly where the entire operation crashed.
Hard crash.
Because automation is fast when it's just manipulating text, but they built a verification phase into it.
They had to verify the changes.
Right. The agents attempted to build the C++ projects to verify the edits. And suddenly, 4 of the 8 agents just aborted.
Just died.
My immediate assumption reading that was, oh, the bots wrote invalid C++ syntax and the compiler rejected it.
That is the natural assumption, but it was completely wrong. The file edits were flawless.
The bots did their job perfectly.
They did. They aborted because of severe resource contention.
Resource contention on the machine itself.
Right. C++ compilation is notoriously hostile to system resources. Parsing templates, generating translation units. It takes massive amounts of CPU cycles and memory.
So 8 bots doing that all at once.
They completely starved the host machine. The operating system just started killing processes to survive.
If we connect this to the bigger picture, it highlights a massive blind spot in automation.
Oh, huge. Delegating text edits is an I/O-bound task. It's cheap, but verification is CPU and memory-bound. Hardware sets a hard physical limit on automation.
Here's where it gets really interesting for me. Think about a crowded room.
Okay.
Everyone tries to leave at the exact same time through a single doorway. Everyone successfully walked across the room. That's the parallel file edits. They did the work.
Right.
But when they hit the doorway, the compiler, they get wedged in the frame and the whole system collapses.
That is a perfect illustration.
Yeah.
Parallel edits, sequential builds. That was the crucial lesson they recorded. You can run as many agents as you want to rewrite source code concurrently because disk I/O handles it fine.
But they have to form a single file line for the compiler doorway.
Exactly.
But since the agents actually finish the edits before crashing, how often do we mistake a system resource failure for a coding failure?
In poorly monitored pipelines, constantly, teams will throw away valid pull requests because a transient resource spike caused the build agent to time out.
They just assume the code was garbage.
Yeah, you cannot trust the final binary state of an automation run without actually investigating the layer of the failure.
So they implemented the sequential verification queue, the doorway is cleared, And we move to the final sweep of the evening. Let's look at the final scoreboard.
It was highly successful. 7 projects required actual code interventions, and all 7 passed strict release tests.
Like the XPTT and CPP project, right?
Yes, PTN-TP. It had 10 functional casts fixed and then passed 99 out of 99 tests.
That's awesome. And the 19 projects with stale docs.
They were updated to the modern project-enabled clang-tidy flag.
So by the end of the night, 21 projects were pushed to the dev branch with 0 real findings across all 27.
But there was a late-night scare.
Right. During the final verification, 2 bugs popped up out of nowhere. A spudlog SIGSIGV in debug mode, and a bizarre netlist-x CDA object bug in CMake.
And if you've just run automated scripts everywhere, your first instinct is...
The bots broke the code.
Exactly. But the developer handled it perfectly. They utilized a pristine Git checkout.
A totally clean, unedited version of the repository.
Yes, they ran the build process on that clean version, and the bugs reproduced exactly.
Wow. So the automation didn't cause the failures at all.
Not at all. It simply forced the compilation of edge case configurations that were already broken.
I mean, a debug-only segmentation fault usually points to an environment mismatch anyway, right?
Usually, yeah. But the CDA bug in netlist-x was probably due to malformed CMake target properties that only showed up because the pipeline heavily scrubbed and reinitialized the build environment.
The bots just exposed pre-existing fractures.
Exactly.
So what does this all mean? When we look at this one evening sprint, the numbers tell a very specific story. Out of 27 projects, only 7 actually had decaying code, but 19 had dead documentation.
19 out of 27.
The REDM were actively lying to the users. Is keeping documentation accurate actually a harder problem for developers than writing the code?
It reveals a systemic reality about how software ages. Code executes. It has a strict, immediate feedback loop.
If the code is bad, it crashes.
Right. The compiler throws an error or the analyzer fails the build. The infrastructure forces you to maintain the code. Documentation, though, it has no compiler.
It just sits there.
The system does not care if a flag mentioned in a readme was deprecated 3 years ago. The build will still pass.
Oh.
Because there's no automated enforcement for docs, it relies entirely on human discipline. And at scale, human discipline always falters before the code does.
It's a harsh truth, and it perfectly encapsulates this massive undertaking. We watched a developer fight a silent MSVC failure in the dark, navigate AST traps with no except lockboxes, and wrangle parallel bots that choked out their own hardware.
And the ultimate takeaway from the notes is profound. clang-tidy, or any tool really, is only as good as your setup and your safety nets.
If you don't manage the context, the tooling is worthless.
100%.
And before we wrap up, I want to leave you with one final thought to mull over. Tonight, we explored a scenario where a human engineer deployed automated agents to clean up human errors in C++.
Yeah.
But as we move toward a future where AI agents are writing the majority of our code, what happens when those agents start introducing their own weird functional casts or hallucinated docs?
They'll do it at a massive scale.
Exactly, a speed and scale that outpaces any human's ability to run a manual evening sweep. So when the AST traps become too complex for a simple no-except block box, who or what is going to write the static analyzer capable of cleaning up after the AI?
That really is the next great bottleneck. We're automating code creation, but we haven't automated architectural oversight yet.
Something to keep in mind the next time you find yourself fighting a build script. Thank you for joining us on this deep dive. We'll catch you on the next one.